Ladies and gentlemen, welcome along to your weekly SETI seminar series. Today we're lucky enough to have Bruce Damer, who's a PhD student at Stanford, and he's working on an evolutionary artificial intelligence simulator. Bruce worked for 10 years at NASA Ames, working on 3D simulations and simulations of future NASA missions. Before that, he worked at a company called Avatar.
Oh, I worked in the sort of virtual world's avatar world.
Virtual avatar world, which James Cameron has stole from him quite successfully over this Christmas holiday. And before that, he worked on graphical user interfaces for Xerox. Today, he's going to talk to us about his project at Stanford, which is called Evo Grid. So if you'll join me in welcoming Bruce Damer.
Thank you. Thanks, Adrian. Thank you, SETI.org, SETI Institute, for having me here. I'm actually doing the PhD in London, but I'm happy to go talk at Stanford on this. So no worries. In fact, you're looking sort of a late model student. I started this project in 1985. I was at University of Southern California. I had a VAX 11750 on the ARPANET. I thought, and a Tektronix graphics display, really high end, when I can do this. And then I looked in the literature, and there was a book by a guy named Johnny von Neumann in the mid-50s about self-reproducing automata and some Russian stuff, and I realized I can't do this kind of thing now. It's just, there was no field. There was no field of artificial life, nothing. So I said, I better wait. I just didn't realize I had to wait 25 years. So I waited 25 years, gone back, actually to my original advisor at USC and a number of other people who said, yes, we'll support you, and try to get the PhD done by 50 on the original idea, which is this EvoGrid idea. And what it is building an origin of life simulator, and all that implies for life, the universe, and everything. And this project is in the memory of Douglas Adams because he was a speaker at my second conference. I had a conference series on this kind of theme, and he passed away. And so I'm dedicating the project and the number 42 to Douglas. So we're sitting in the SETI Institute. You take the S and the I off, and what you get is ET. Is it a coincidence? I think not. So if you're asking about ET, how many, if any, are out there? That's what this institute's for. How many are on the move? How many are decided that they're going to go out and explore and try to meet and greet? How did they figure out how to do that if they are on the move? Perhaps how could they have figured it out? And how can we do the same? Well, I think the great guidepost of SETI searching for the I love Lucy kind of SETI, i.e. the detectable people who are transmitting, is of course the Drake equation. And anyone here who hasn't seen the Drake equation in this room? Probably not. So no explanation is needed, but there are all these terms to estimate the number of civilizations in our galaxy with which communication might be possible. And here are all the terms that still are very much our guidepost. But recently I decided to kind of write extensions to the Drake equation. I'm sure this is a popular pastime amongst ET nerds. But so this is for the ETs of the bold to go where no ET has gone before kind, the ones that want to travel. So if there's an ET civilization out there, how many of them have gotten to this point where they're actually journeying, and maybe not astral projection, but the real kind of physical journeying, the hard stuff. So the terms are, I got my, only at the SETI Institute would you have a laser pointer that looks like a original Star Trek communicator, but I hold it up as evidence. This term is the fraction of civilization who support visionary geeks like us in this room, wacky individuals or collectives, because it may not be individuals, who are not solely committed to mundane productivity. Like your general, they're not your cubicle office worker, but instead they're hooked on this boldly go escapade. F $ is the fraction of those civilizations whose visionary geeks are not only out of the closet, but are able to get funding support. A very small fraction of, guys, another survivors from the Santa Cruz Mountains. You gads. You're right at the beginning too. F time plus N is the fraction of civilizations who are willing to fund visionary geeks for an indeterminately long periods of time. And this is, of course, a much smaller set of sentient civilizations. F big T is the fraction of the above civilizations which are willing to pay for large-scale versions of the geeks' products for very long periods of time. And this isn't, Google isn't in practical products. These are probably spacecraft. And FM, a fraction of the above, they're able to remember what it was all about and handle the end results or lack of results in a mature way, i.e. not killing off all the visionary geeks and burning the fleet. So for those who are boldly going, this may be whittle it down quite a bit. I'm postulating here, because this is the only thing you can do in this field, that in order for visionary geeks to do the boldly go thing, the very few that are maybe one per galaxy, perhaps, allocation, they have to do the following, they have to go through the following 7 steps to do the boldly go thing. They have to actually start out, I think, having the concept of abstraction, math, as all good geeks have. And they have to learn how to adapt their brains or build machines to render these abstractions into a simulation, i.e. conceptual worlds. I feel it sort of intuitively that if you can't build simulation, you can't build spacecraft. That's what I've been doing for 10 years with NASA Ames across the road here. But they also have to have acquired understanding of their own evolution. Where do we come from? And be allowed to postulate that they came from somewhere other than a creator, and say that publicly without getting all their heads cut off. Hi, Seth. Chair right here if you want it. Right in the front. There's one, oh, there's a chair for there. There's one here, one chair there. There's another chair right here. Come on in. Wonderful. I think we're squeezing in. Everyone got their peanut butter and jelly? Here's one here. So these visionary, we're talking about visionary geeks, part of a rare civilization that actually funds visionary geeks, and this visionary geek ETs are deciding to do the whole crazy project of boldly going out to look for others, not just transmitting willy-nilly. They want to build spacecraft, and how few civilizations do that. And for those who missed it, here's my additions to the Drake equation that show how few relatively ET civilizations would have visionary geeks that are funded for almost infinite periods of time to do these projects. But those geeks have to understand abstraction, they have to understand evolution, and then they have to understand that they could marry the mechanisms of evolution with the tools of simulation to play around with primordial soups. Why would they play along with primordial soups? Because it may be that primordial soup simulations can do innovation faster than we can do with our brains. And there are tremendous accelerators for this. So then the visionary geeks have to apply this magic combination of evolving a viable biota that can live out of their homeworld, bioplasmic machine or both, and take them or their replacements out into the universe. I.e., if you want to boldly go, you may have to have things that are better than you, better adapted than you, to do the boldly going. Last 3 things they have to do: they have to have a good working knowledge of the bits of the universe where they expect to send their bio-universal machines or bum selves. And they have to have the time to put it all together. For a visionary geek ETs to get your bums in simulated gear, fabricate them in atoms, and dispatch them to boldly go forth and multiply. So this is even harder to do. The last point is when they finally get there, some not small time later in a parking orbit above the Earth, the ETs honk and wave, "Yo, down there, got anyone crazy enough to be working on what we just did? If so, send them up." So our visionary geek ETs will have answered the key question of the universe: are there any other bums like us out there? Now back to SETI, which is finding a needle in the cosmic haystack. Now enter the EvoGrid, which is kind of like SETI, but turned on its head. And you'll see why in a second. Because the EvoGrid first must create a haystack, a simulated virtual world, an origin of life simulation, in the hopes that a needle spontaneously appears in it. And the needle is emergent phenomena, self-organizing phenomena, virtual critters, if you will, and that you can also find the needle. So there's an inverse SETI going on in the EvoGrid project conceptually of you've got this massive particle simulator and you hope things are emerging within it, but you have to be able to see them. So you have to actually do the SETI at home distributed computing thing, and you'll see that a little bit later. So here's our needle we managed to find. So let's take a look at the concept of the EvoGrid. And this is a movie that we did for YouTube for the public that kind of does it. It shows you the evolution of new virtual critters and then testing them out in a test tube to see if they'll actually work using molecules. So let's take a look at this. The EvoGrid, a whimsical view of a hypothetical evolution machine. Here we see the EvoGrid simulation cube underlain by processors, lots and lots of processors. And as we come in, we see there's particles in the cube. Particles are starting to interact. And then suddenly we see a doubling of the processors, and then a doubling again. And we're starting to see some interesting phenomena. So let's dive in and see if we can see something happen. And it looks like with our little observer camera, we're finding something interesting going on. A little bit of self-organization is happening here. Oh, a vesicle has formed. And it's got something inside of it. Let's go on a few billion generations and we have something a little more interesting going on in the vesicles. And a little bit more structure in this one. And a few billion generations later. And oh, we've got a little bit of behavior going on. It's more of an entity. And we've got a really complex entity here. Let's push this along and put it into our scanner. The scanner's going to take it apart digitally. It's a digitally evolved being, of course, and build its little capsule of XML data. Now we're going to transmit it to our nifty nanofab. Our Acme nanofab is taking in CO2, ammonia, and good old water, H2O, and it's going to fabricate our digitally evolved entity into a creature of chemistry, making sheaths and strings and reacting parts and channels. It looks like our creature is finished. It's being printed, and out the end of the glass tube will come our fabbed entity, ready for a swan dive into a beaker. And in the beaker is the formulated chemical soup designed to be like the original Sim cube. And let's see if our creature is recognizing the chemicals, and it's running the algorithms, and it's swimming off. So it seems to be off to a good start in a new life in the world of the molecule. So this was our initial fun little EvoGrid movie showing the concept for the public, and we put it up on YouTube, and it's getting lots of views and lots of weird comments. And that really started us out in 2007, 2008. And there's another movie at the end I think you Space Weenies will really love, which we'll get to after we show you what we're building. So I showed this to Freeman Dyson at the Institute for Advanced Studies last February, and he said, well, nature is more messy. Nature's not clean and neat. You're showing the movie, as you're showing the movie, cells are more like dirty water surrounded by garbage bags. And of course, you recognize that quote from his book on origins of life. So, building life the hard way. I'm going back here. You'd think, of course, building life out of molecules in the universe is sort of the easy way, but let's see if the chemists think so. So you've got all these wonderful goodies that have come into the Earth, down into the oceans, black smokers, hydrothermal vents, great reaction points, all kinds of goodies, but you had a big computer called the Earth that could do this job. So when humans started to try to do origin of life chemically the hard way, this was one of the first experiments, the Milleri Experiment from 1953, where they got some amino acids to form in the simulated early Earth's atmosphere and oceans. This is a wonderful diagram that sort of almost looks like a great big glop, but it's showing the movement up toward the prokaryotic cell from sort of blobs, sort of showing, assuming that this is sort of a nice orderly process. These aren't all stuck together. It's just showing complexity as you get toward prokaryotes up here over a long period of time. So I decided to say I'm going to go find the people who are trying to do chemical origins of life. And the first place that I went last year is the University of Southern Denmark, a very foggy place called Odense, where Hans Christian Andersen is from. And this fellow here, Steen Rasmussen, you may recognize from Los Alamos Labs in the original A-Life movement of years ago, has gotten himself 4 to 5 years of funding to do chemical protocells. And in their lab these are some of the drawings of the actual chemical protocell models that they're going to start with. This is their computing equipment. It's holds little vessels and vials and hanging droplets of fluid, and reacts that fluid, and then they test the fluid to see if anything's going on inside. That's chemical computing for you. This is the model that Steen came up with for how to make the first human fabricated, from scratch, not from pre-existing bioparts, chemical protocell. And it turns out it's little globules of fat with layers of what are called surfactants on them that things then attach to. So it's kind of a cell inverted. And this is their model, that these globules of fat will get a DNA and rubidium clusters attached to them, and the DNA will be, the globules will be heated when light is shined on them, shown on them, and you'll end up with metabolism within the whole system, division, container division, and then going on and on and on. So far they've gone from this step 1 to step 2, and they've managed to get this to happen in the lab. But how easy is this going to be? This is really hard. If you go to the Flint Lab in Denmark and you see the pace of experimentation, and they'll grind through a whole series of heating and vibrations and heating of the single droplet, and then they'll sample it and they'll go over to the $1 million microscope and they won't see anything. It's this very, very arduous grinding process. Penny Boston, who's a frequent visitor at a conference that Seth and I are both at called Contact, which is coming up in March, come to Contact, last year said, look, she represents sort of the other camp. There's one camp in this project that says, simulate a chemical origin of life, because if you can do that as a simulated chemistry, it will help us figure out how to do it in the real chemistry. Penny says, don't try to do a virtual chemistry. You'll never get there with the computing power. Try using abstract universes. And this is Freeman Dyson's approach as well. All that counts is if you can demonstrate a method for supporting ever-increasing levels of emergent complexity. She basically concluded, you need this to originate and evolve complex life and civilization. Big computer, lots of time. Well, let's examine a little in more detail. So Penny would say, well, the big, in science, it seems like big science is always aimed at great dark gaps in human understanding. So the James Webb Telescope is going to look at the dark ages of the universe before light came in. You had Crick and Watson looking at what is the mechanism to code for cells. It was a big dark gap in knowledge. SETI is looking at this huge dark gap. Is there anybody else out there? Well, it turns out that in origin of life biology, the huge gap is between the molecular soup, which has fairly big juicy molecules in it, and then the minimal cell, the big gigantic machine that is a functioning cell. And this is just some of the parts that you have to have in place for a minimal functional cell. as understood by biochemists. So how do you get from your basic simple little molecules to a machine? This is a prokaryotic cell structure that is massive. It is absolutely massive. The creationists called this the problem of irreducible complexity. I think that this gap can be penetrated and have light shone on it by the power of simulation, and that's what the EvoGrid project is. Now, to show you potentially how to jump the gap, one of the things that's understood now about these chemical soups is that chemical soups are really powerful. They do all kinds of things. They have super duper capabilities. And one of them is you can get microenvironments forming really quickly. You can get then disruption of the microenvironment, say salinity or something disrupts it. You have all this junk parts left over. If you got the microenvironment, these experiments are all going on simultaneously all the time. It's massive. It's a massive amount of computation. If you manage to get a protocell, it's supported by the previous levels of the microenvironments that are there. This is known as open-ended emergent complexity. And you have to have the junk from the previous levels still around that are going in and out and supporting the more and more complex levels. So it's a multi-scale, multi-physics environment, ordinary bathtub chemistry. It's amazingly powerful, and we're only just starting to understand how much. So let's take a look, though. This is from the Inner Life of the Cells animation done by Harvard. I'll just run this for a little bit. But the machine that is the living cell, I mean, it is astonishing. These are very cinematic views of the mechanisms of cells, but this is actually accurately, these are lipid rafts. Lipid rafts are so cool. They're floating around on the insides of your cell wall. These are mechanisms. There's the cell wall, there's a lipid raft, and these are all sort of sensors, detectors. They're like the operating system layer. This is structural stuff in the cell that's growing and shrinking on and forming all the time. This is more structure. I mean, if you could do a cinematic fly through a cell with this kind of production values, you'd see all this going on. Here's the formation of structure. There's my favorite thing is coming up. I think it's the walking protein. Here's a little severing protein that is going to break that structure. It's just perfectly adapted. Here's the famous microtubules. And here's the microtubule disassembling. And here's the famous motor protein dragging a vesicle along a microtubule. Now, it doesn't quite operate and look like that, but isn't that cool? It's walking along. And here's a Golgi apparatus and all this, a centrosome here. It's massive. We're not even looking at the nucleus. It's absolutely massive what is going on in that machine, that one machine. Very humbling. So, needless to say, I mean, this is non-trivial. So when I show this to artificial life developers, they're going, oh no, this is impossible to code. I mean, they're doing Conway's Game of Life and walking creatures and whatnot. This is a massive virtual world, and it's one cell, and it's one little part of one cell. So how do you map this computer onto this computer? I have a collection of these. If any of you know, I have a Digimon computer museum. I have hundreds of old computers, and none of them really can do this, but they're cute. They're cuter maybe. So the EvoGrid, the project of the EvoGrid is, as you saw in the movie, conceptually make a gigantic space that is a digital primordial soup underlain by a gazillion processors, maybe game chips are better, and then a lot of computers looking in to try to figure out what is going on. So this is where it's sort of SETI on its head a little. They're looking for emergent phenomena. So the formation of little carbon rings might be interesting. And then they'd be talking back to a central server which says, oh, cool, in this little stack of frames we found little carbon rings, so we're going to actually make more computing going on in this little corner here and allow more to happen. That's the basic idea. So the secret sauce of the EvoGrid is what's called a stochastic hill climbing algorithm utilizing analysis, feedback, and temporal backtracking. In real English, this is, so control, you've got this simulated frame going along, boom, 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 and you might get a couple of barbell molecular bonds forming down to here. But in the secret sauce version, you decide, oh, I don't like this one, I'm going to stop computing this frame. I'm going to go on and I'm going to compute more frames of cool things with three nodes, and oh, that one died, so I'll stop computing that one. I'll go down here and, oh dear, this one completely broke up, so we'll go back up here. And this one broke up, but this was so cool, we'll go back and sort of randomize this and allow this to go forward, and then we get our little carbon ring. So that's the idea of the EvoGrid. And this is the engine, no need to go into the details. This is the engine blowing up in July of last year, where we started up our first 1,000 atom simulation, and we neglected to notice that the atoms were sometimes inside the other atoms. And it caused a runaway heat, and that was the end of the experiment. So the simulation's done in the last 2 months. We've managed to control the heat problem, and we're running 1,000 iterations of 1,000 randomly distributed atoms in a heat bath with GROMACS, which is from University of Groningen, where I know you spent some time. Those guys built a really great open source tool for 1 second, and we've been producing these massive amounts of data. So I'll go into this a little bit more later, but it's sort of gigabytes of data come out all at once. So if you don't blink, this is a plot of one track, and if you didn't see that the first time, here it goes again, from randomness all the way up. And let's take this apart a little bit. So random, this is where we're starting with our random group of atoms, and these are the weights of scores of frames that came off of this random field and how good they were relative to our measurement. And if we go to the next frame, this line follows up here. That got to 24. Oh, that's good. What does 24 mean? And this one got to 28. So we did a whole bunch of generation here and didn't like those, but we liked the one that went up here. And this one got to 30, my goodness. And it got to just a little over 30. Things are slowing down a bit. And we got to 33, and we couldn't get any further. So this was our winner in the game. That was simulation number 144,204. And what that was we took the size of the molecules that were generated, just a simple, dumb measure. We got one that had at least 17 connections through it. Now, we're not chemists, and we don't play chemists on television, so we don't really know what this means. This is why we have chemists on the advisory board. But this was our computer science-y measure that we're getting ratcheting. We're getting a little more complexity in the system. Now, Peter Newman, my chief engineer, tells me, it means nothing. If we kept running this, it would turn into one gigantic macromolecule and jam up. So we have a bit of work to do. But this is our first run. Happily, we were contacted by a dear friend down at Cal IT2. Doesn't this look like a spacecraft, this building? This is down at UC San Diego. And he said, sure, you can run the EvoGrid on our cluster, our rock cluster. Get it all prepared. So now we're preparing it. We'll be running it on a multi-gazillion gigabit network. They have beautiful projection displays, et cetera, et cetera. So we've been talking to them for a couple of years now. So it looks like February that we'll start running here where there's serious disk space. Oh, and by the way, part of this is inspired by SETI at home. We're going to be having EvoGrid at home, where your screensaver will be looking for the complexity in the particle field. So back to boldly going where no earthly ET has gone before, which was my original challenge. This man keeps reappearing. I don't know why, but he seems to have had all the ideas long before the rest of us. Of course, when the big alien ET craft does come into orbit, it'll probably be the Freeman Dyson, HMS, etc. He will have been other places we haven't. So Freeman Dyson's trees. Now Freeman, before I roll the tape, had this really neat concept. You know how people kind of tell jokes about Freeman that, he will suggest that we could evolve trees that would give directions to lost hikers, these kinds of things. But he had one really cool idea, which is fairly old in science fiction, but he enunciated it well, which is there are more sort of inhabitable solar areas in the solar system, surfaces on the Oort cloud, comets, asteroids than there are on planets, and therefore wouldn't it make sense to create or evolve forms of life that can live natively on those surfaces if you want to kind of green the solar system and whatnot. So somebody called them Dyson's trees. So we made our second EvoGrid movie inspired by Dyson's trees, and this is where the Boldly Go comes from.
The asteroid eater.
I'll hold this up.
Fantastical concept inspired by Freeman Dyson's trees. Here we see the EvoGrid simulation cube, and we have a virtual asteroid, a model of an asteroid in space coming in, being introduced into our cube. We doubled our processors and we doubled them again to put computing power behind the virtual evolution in the cube. What do we see on the surface here? We see critters have evolved to live on the surface of our virtual asteroid. We're coming up on one of these critters now. It looks like a fine specimen. We're going to lift him off, and we're going to send him on a journey. The journey is going to take him to our scanner, which is going to take him apart digitally and allow us to send him to a higher calling.
We asked Wallace and Gromit, and they said we could use the rocket, so it's...
And our virtual creature is approaching the scanner. We'll get lined up. Scanned, all of his digitally evolved parts are going to be packaged up in a new form. And our creature's all packaged and ready to be transmitted to our nifty nanofabricator, which is housed on a rocket. The rocket is getting set to take off and boost into space, carrying its precious cargo of terror and artificial life. And our rocket's in space going to the far reaches of the solar system to an asteroid which is very much like the one that we simulated in the EvoGrid simulation cube. We're going to set down on this real asteroid. And our nanofabricating rocket is starting up with its sources of hydrogen, ammonia, and carbon dioxide, and is fabricating our digital entity into a creature of atoms. And the hatch swings open and the gangplank comes out. And it looks like, yes, we've got a creature it's made out of atoms. Oh, we have another one. We have two creatures fabricated out of atoms. Two small steps for virtual creaturehood. And they're opening their solar collecting energy wings. Moving around a little bit. Oh, we see a little bit of an intimate moment there. Oh, there's an offspring. Another little one has come out. And we're seeing generations coming out. And the nanolichens and the creatures are populating and covering our asteroid. What do we have here on the left? We have our spacecraft coming, our human crewed craft in for refueling for some more cosmic milkshakes for the human crew. And as it refuels, it's taking advantage of a new form of biota which now lives in the solar system and allows human life to travel farther than it ever has gone before.
So, this brings us sort of full circle. If we're brewing up aliens in the EvoGrid, digital aliens, are they really alien? I mean, they won't be carbon chemistry, right? They'll be something else, especially if we follow Penny Boston's advice or Professor Freeman's advice into abstract universe, they'll be pretty abstract. We couldn't make them out of atoms. But are they alive? You know, are they now protected under the Endangered Species Act? So perhaps if you turn this the other way, maybe the EvoGrid, future EvoGrids with infinite computing power in 100 years might be a new kind of SETI telescope, where the universe, asking the question, where in the universe might life arise? So for example, if you got a really good model of the Martian ice cap from Phoenix, if Phoenix got revived for years to come and did a huge amount more science, we could model the Martian ice cap and put in, you know, the ice and the compounds and whatever was in the atmosphere, and see if ever life forms emerged in our virtual Martian ice cap. So it's kind of a telescope saying, model this and see if something happens. And maybe what kind, you know, would large, intelligent, high IQ civilizations come out of Martian ice, sort of the ice people? You just keep running your simulation. Then you might know where to look. Or what if you had alternative universes and you decided that the EvoGrid project should consume all of human, you know, funding and potential for the indefinite future? Then you could simulate all kinds of abstract universes and then build a kind of a continuum and say, well, our universe is pretty sucky for creating life, is this a little bit, but if you had this other universe with this other physics, it would be rife with life, to quote Seth. So the EvoGrid could kind of generate all these plots and dimensions about, you know, universes that could have lots of life and it'd be much more interesting than us and whatever, and then there's our sucky universe, and then there's universes that just have no life at all. I mean, this would be if you had an infinite amount of computing power. And this came from a conversation we had at Contact 3 years ago. If you had an EvoGrid, maybe it becomes a way to communicate with ET. Perhaps if ET are AIs, ALs, machines, they come into orbit, and you know, we send them I Love Lucy or serial communications or, you know, Google News, they're never not going to grok that. But what if the EvoGrid is this massive array of, you know, artificial life that groks their signal, which is massively parallel coming down, and it's massively multi-agent complex. It's like a big complex dump. It's like every neuron they've got, they throw at you. Well, we couldn't possibly have a signal lock with that, but if we have an evolving system, it would get this signal and it would start to evolve and create little virtual organisms and virtual detectors that would finally do the signal lock with this big brain that's up in orbit. So maybe this is another reason to fund EvoGrids, that we could talk to them via adaptive virtual creatures. And if they got that kind of signal lock, well, they might spare us the bulldozers building the intergalactic bypass. And this is an important point here. You know, we don't want those great big yellow spaceships to appear. And then this is the most wacky thing. If you think these are wacky, this is the most wacky thing. And we talked about this at Burning Man 2052, or, you know, 2012, the world's not going to end, but maybe we could arrange for it to end at a later date. And one of the ways to happen would be, say, in 2052, we drag a quantum computer, go to Fry's, buy a whole bunch of quantum computers that are just available. You know, they run Microsoft Word and Excel just about the same speed as a computer of 1990, but they're quantum. So, untold memory to run to save a single Word document. We drag the thing out to the playa at Burning Man, and we'll put a big sign on it that says, well, actually, the quantum computer is so small I can barely see it, but it'll be sort of masking taped onto the back of a gigantic button on a gigantic spring, a red button. And on that button it will say, do not push this button. We really mean it, do not push this button. So there's playa people, and it's 2052, it's mid-century, they're doing back to the 50s or something, and they've got all their giant, you know, anti-gravity 52 Fords and Chevys and whatnot, and they've got to push this button. You know, it's a Sunday night, it's almost over, and we're going to just like line up all our old 100-year-old cars or whatever and get this button pushed, and what will happen is it will start the reactor. So it will dump our best EvoGrid simulation into that quantum computer, and once it arrives in that quantum computer, we disclaim all responsibility, because the quantum computer cannot contain any computation. It is computation. The quantum qubits are reality. So whatever goes in there and learns how to organize that reality it can do what it wants. So at Burning Man, people really wouldn't notice much because they're already kind of in an elevated state. So the quantum computer would start to get bigger and it'd have like glowing, colorful things around it, and then it would, the containment walls, which were so carefully built by the engineers at Fry's, and we know how good they are, would break because the virtual organizations, virtual organisms in the qubits would go, oh, container wall, I'll just reorganize that and I'll get my way out. So what will happen is all these virtual creatures, which are digitally computed, but they're reality because they can change matter and they change electron shells or whatever, they just escape. So at Burning Man, the sky goes psychedelic and everyone says, this is the best burn ever, you know, everything, and galaxies change shape and stuff is going out, and it's the end of the stock market, it's the end of financial shenanigans forever and everything. And so then the universe just turns on, you know, and they temporarily you'll see Timothy Leary go across the sky. And so that could be the ultimate goal of this project. Anyway, so that turn on the universe, of course the universe goes, what is going on? You know, it looks back into all the memory of all the sentient beings and it says, this is what has been happening here, and I'm expanding, and the person should have pushed that button, and now we're expanding faster and faster, and we got to organize, and we got to stop this expansion, and we'd all be in a lot of trouble because we hadn't done our jobs. So through this project, we will find, and this is the challenge, find out the power of primordial soups. Remember, I mentioned this in the beginning. There already exists primordial soup. It's a Campbell's product, and I think it says a quick meal in 4.5 billion years. And just acknowledging the wonderful people who made this possible. Richard Gordon is a professor of radiology and embryology up in Canada. We had a conference in 1997 when I was getting back into the artificial life field. I said, okay, I got to meet everybody who is now in this field. So I formed a conference series, and I created the most strange attractor for them at the time, which is I'm going to do a conference at the Burgess Shale. And if you don't know what the Burgess Shale is, it's this like city block long cut in a mountainside at about 8,000 feet in the Canadian Rockies, quite near where I was raised as a kid. And in it is this wonderful compressed library of Cambrian explosion creatures. So there's layer upon layer of shale. You pull one of them out like the page of a book, and there's a little soft body preserved critter with the last meal in its stomach. It's an amazing thing. They're about 530 million years old, and it's a wonderful site, sort of a mecca for paleontologists. And so I said, I'm going to get all these people to come out, and we literally hiked up to 8,000 feet with two groups, and guys at Discovery Channel holding giant cameras. I don't know how they made it. And we went and we pulled out pages out of the Burgess Shale book. And one of the people on that hike was this guy. And 2-3 years later, 2-3 years ago, he said, come and help contribute to this book, which is called Divine Action and Natural Selection, Science, Faith, and Evolution. It was a project by World Scientific for 2000, for Darwin's birthday in 2009. And I said, can I write, I'm one of the only nerds in here. This is full of theologians and astronomers and I think Seth, you're in here somewhere. You know, really serious people. Can a nerd write a chapter in here? Oh yeah, we need nerds. So instead of engaging in the debates about whether there had to be a creator to create life, et cetera, which is what this is about, I said, well, I'm a nerd, I'm an engineer. I would approach this question about God's existence by building a God detector. So my chapter is called The God Detector, and right at the end is the proposal for the EvoGrid, which tied into Dick's quotation, the Hoyle's tornado challenge to artificial life. And he basically said, the artificial life community should get down to the basics and simulate an origin of life. So this is how this whole project got started. These are the people who are currently working very hard on it. Peter Newman, who's the chief architect writing the code. Ryan Norkus did all the animations and artwork you saw. We're in partnership with Flint at the University of Southern Denmark. We're doing a special session at Artificial Life 12 in August, if you're going to that. Freeman Dyson's given us a lot of advice. There's about 25 other advisors to the project. And happily, here at the SETI Institute, where I think it's a natural home for this kind of thinking. So thank you very much. If you can't see this, it says, "Are you my mommy?" For having me, and I've left, hopefully, yes, about 10 minutes for questions.
Bruce, if I can start off with the question, can you talk to us a little bit more about your algorithm for growing the a molecule? Can you tell us about how it actually picks up material and how you decide on that?
Well, the algorithm for growing molecules right now, we're just currently populating GROMACS, this molecular dynamics simulator, with a gazillion atoms, and GROMACS does the work in terms of figuring out what bonds with what. And then we dump the state out of GROMACS and look. Actually, in the earliest version, we're actually forming the bonds ourselves, but they're not quantum dynamic. That's pretty simplistic. But GROMACS does the work, and then we restart GROMACS. We decide what was interesting in that frame and then start it up again. And the creators of GROMACS were initially sort of said to us, "You're doing what?" You know, that kind of thing, because they don't. And the previous packages we tried, they blew up trying to constantly reload. I think you run out of memory if something like that happens. But so this is the state we're at, which is very, very limited. And now what we're looking at is doing experiments. And if I can show you, there's one. Yeah, I'll just pull this up. GROMACS can do wonderful things like the simulation of water ice forming. And if I can find this, there it is. Let's see if it runs. So this is GROMACS at work. And this is water molecules being simulated and gradually cooled. And then crystal and ice is forming in all its various shapes and forms. And one of the experiments that's been proposed for us in the EvoGrid initially is to have gravity pointing in this direction and have a surface, do this experiment, and then see if our little water ice crystals float to the surface. Now what's interesting is then you have emergent physics, because buoyancy, you don't know what buoyancy is before you come in here, but because the crystals are less dense than surrounding simulated water, they will move to the surface. So buoyancy is an emergent phenomena, a physical property, but it's an emergent phenomenon of the simulator, which is what this kind of simulation is really intriguing for. I think a couple of questions in the...
I just have one more follow-up. I'm going to be greedy here. Sorry, Bruce.
Yeah.
So would it be possible then, this is obviously going to blow your current computing out of the water, but instead of choosing your fitness level based on the size of the molecule, in future generations you could test molecules against other molecules in the same environment and have them compete for resources?
Well, yeah, and in fact, this is what I would, where I have to really be careful, because this is pre-evolution. It's before any Darwinian natural selection's happening. What we're hoping to see is, say for instance, a lipid bilayer forms would be great. A vesicle forming would be great. And then you suddenly have these megastructures. Then you have to switch to different physics because you don't want to simulate all these megastructures. So now you're simulating vesicles. But do the vesicles then compete for resources? And this is what the chemists are trying to find out. Can those vesicles grow on their own? Can a vesicle with a certain thing inside it be a little bit more long-lived? And then you might have Darwinian natural selections kicking in. And that's what we would hope we would get to, is something like that, or an RNA universe occurring, strings of RNA that are replicating.
This reminds me of my first tenure with Origin of Life Research with the Rockefeller Molecular Theory Lab. And our lab was basically theoretical computational chemists. And what we did for NASA at that time was NASA was seeking interstellar molecules. And we basically ran our computational physics and said, you'll find this, you'll find that, you'll find this. Naively, when I came there, I thought that they would find a molecule and we would tell them what it was. And after a short period there, I learned that we told them what the molecule was, and then they would find it.
Yeah.
And in fact, they would always say, the proof is in the pudding. So my question to you is, where's the proof in your pudding?
Yeah, this is why we have 25 advisors, because we're just at the very foot of the mountain and trying to define this class of experiments. So Doran Lancet, Alan Shapiro, was he working with you?
No, but I'm
Familiar. So we've literally gone and asked this very question to a lot of these people, and this summer at A-Life 12 is going to be a whole session on if we can do, because people have built these, artificial chemistry experiments for years, but they're so small scale that and the budgets run out and grants run out. The idea is to use grids and open source to finally be able to scale this stuff up and build a common framework. So for example, the EvoGrid has a piece called the ChemoGrid, and the ChemoGrid is right now GROMACS, but it could be any molecular dynamics or a coarse grain simulation. You could pull it out and put another one in or run two at the same time. We did this for NASA for 10 years. We ran physics-based rover simulations, rover terrain. And we had 4 physics engines at one point to do soil, machine contact, rigid body, whatever. So it's old territory for us, but we left NASA with this great framework that they can use. It's open source, it's got scripting and all new modern stuff. So the EvoGrid really is what we're hoping to be a gift to the community. Say, plug in you can go to a website and say, I want a trillion atom simulation. I want to run it for 5 nanoseconds, and I want the starting composition to be there and all the physics sliders, and move them and then push submit and then run your experiment. That's the dream. Doing origin of life work is a real kicker sort of intellectually to get people thinking about all the problems. But if in the end we produced a ChemoGrid that people could use, I think would cause tremendous advancement in material science, chemistry, biochemistry. The long-winded answer.
Well, we're on the theme of history. I actually did a PhD thesis on the origin of life, prebiotic evolution in '77, and that's how I came to NASA with a fellowship in the first place. And we also did some work in protocells ideas, again in simulation theory about 10 years ago, and I developed a system called molecular network, MolNets, which was actually use some peculiar way of creating structure, function, relationships. The key point is that's the difficulty. The main difficulty is to build the rules at the bottom that are somewhat analogous to the rules of physics, but yet not. But you cannot make them like the rules of physics. So you've got to make them so that they can create this artificial world without putting in the solution. You want to really be honest about rules that are, totally not compatible, but analogous again to the rules of physics, yet simpler possibly.
Yeah.
You don't know. I don't think that you really have to simulate a chemistry accurately, and that may be really way too difficult and perhaps not get you to what you need. Because an artificial life does not have to look like artificial life, and yet, it doesn't have to look like real life. The equivalent of an artificial life protocell may not have to be like a protocell. But so the idea that artificial life, in some sense, is real life from the point of view of structure of its own right, without having to imitate what is physical life. Anyhow, we should talk. There's a lot of stuff I want to communicate with you.
Points. I think Carol, did you have a?
Actually, Adrian asked my question.
Oh, okay. One of the points of this project is a lot of faith, because of the whole Moore's law thing. But simulation, 10 years ago, our first rover simulation for NASA was really simple physics. The rover actually started to break dance because it had again, sort of an occlusion with the surface, and it was just dancing around like crazy because it's an energy system. And it took us about a year to figure out how to dampen that down and make that look real and run real. And then 3 years ago, working on a robotic lunar rover project, we actually were able to get a design where we had wheels with the right amount of sort of torque on them, a huge amount of preparatory work, and the right tines on the tires, kind of like the Mars Exploration Rover a little bit, go down this really simple slope, crater slope, and we watched how it moved along and then it started to slip sideways. And somebody who's at JPL who really knows this kind of stuff, they're designing the Mars Science Lab, he took the stick and he was backing it up and he said, give me a vertical surface. It's a rocker bogie mechanism, which is this kind of two-wheel, one-wheel thing. And he backed it up against the virtual wall, a vertical surface, and the back wheels sort of clambered up the wall, and he was able to mount the wall. And he said, this is a true rocker bogie simulation if you can do that. And it was the guy that came up with the rocker bogie. So it's like, wow, after 10 years, we sort of got to the point where somebody stick handled the thing and said, this feels real enough for me to maybe at one point help us in our sandbox simulations and in designing these things. So it's like, that's where my faith comes from.
Yeah, I want to ask about tractability, because it all sounds so great. You've got lots of computers, but the reality is, and I think it really follows from earlier questions, is that these things are not nearly as tractable as you think they are. And you might think that maybe I've got 1 billion computers on my Evo Grid at home, and it turns out that's not even still remotely enough time. And so what I was going to really ask you was, perhaps it might be better to look at a slightly simpler examples. So, one of the things I always think of in biology is that surfaces are really important. And perhaps given that there's some new information that suggests that, again, some types of rock might be better at generating vesicle surfaces, that you might look at doing things like random rock surfaces and seeing whether, in fact, you will get the right alignments to naturally, form things. And that would be much more tractable against a whole lot of computers than trying to provide a prebiotic life system, if you like. So I wonder if you thought about that. Have you done the sort of, even using your early simulations to say, well, given I've got 17 molecules with one run, really would 1 billion computers make any difference or not?
This is one of the big open questions. David Deemer over at UC Santa Cruz is promoting the idea that we do the wet-dry rock cycle that he's doing in his experiments to form vesicles that then collapse into a dry state and then reinvigorate with a wet state. And then they find that actually in chemistry in the lab that you can get long-string polysaccharides that are forming and that are also infused into the vesicles. So his whole promotion of the use of this platform is just focus on this experimental framework. And I would be happy to, it would be thrilling to be able to actually support that kind of research with a framework like this. And if we could, then perhaps you're right, we can move on to tabula rasa origins, which is what we're talking about here. I'm kind of, in a sense, putting the bar for the project at the very high point in the hopes that some wonderful billionaire with a checkbook handy might do these things. But you're absolutely right. I mean, it may be that the community that is interested in this thing getting built will say, let's start with some more contained experiments.
Well, what I'm concerned about is that you would probably need to convert the universe into computronium to make it work, right? And
that's right.
That's the concern that I'd have in terms of tractability.
Or wait till Burning Man 2052. You had somebody...
Well, I guess I've got the mic. I just wanted to make a comment on your comment, because I've been sitting here with, your wonderful presentation, but the reality of the complexity of that problem, and having worked on the origin of life as well, and seen all of the debates in the field, it seemed to me that it would be very interesting. I think you've really got an angle, and for example, that you might take kaolinite clay versus montmorillonite clay, and then you would be able to go to the experts who have come up with two very different theories, right? You could go to Graham Cairns Smith, work with him on a kaolinite clay model, though he may be rejecting kaolinite. I'm not sure where he is with that. And you could go to the people who have worked with montmorillonite as an unstructured surface And if you modeled both of those and you compared them, but you would have the experts as resources, and David Deemer and the WetDry Cycle, that's another really good idea. But I just think that's a really good direction, and there are probably a lot of examples.
Question. Do we have a question over here?
Did we have a question here?
No.
We have one at the front here.
My question, Wanda Davis, NASA Ames. My question actually follows up on the previous speaker, and that is origin of life has been presented basically to me in two camps. It's either a function of the soup or a function of the substrate. And it seems like your procedure here is a function of the soup. So I'm wondering if you can, if you've given any thought to it being a function of the substrate, which I see you did in your simulation with Dyson, but can you curtail it to only be a function of the substrate? Because my experience with life, as I know it, is that we're a function of a substrate.
I think it's again, it's a very good point. The initial design of the EvoGrid was actually going to be a gas lattice model where we could have basically denser matter, where computationally it would be possible to do this and basically have matter stacked up along the lattices and in the nodes, saying you can't go any further because now we're at a hard surface, or we're now getting diffusion off this surface between a liquid surface and a gas. And everybody I went to said, you need to go to a tuple space, you need to go to a free space, because there are all these boundary problems in gas lattice, and there's 20, 30 years of research in gas lattice. And so we went to this tuple space, and then we said, okay, what's a good molecular dynamics engine? And we found Gromax, and it was like, gee, we're really starting, we're going to start with aqueous sort of level. And it is my dream to also be able to represent solid and gas phase somewhere in there. But again, it's like the computing that is needed and the architecture that's needed. So I completely agree with you that there's a lot. Well, give you an example. It's about 100 computers run for 5 days at the University of Colorado at Boulder last year to do a 1 millimeter cubed simulation of a sort of aqueous phase, and they did it for 2 nanoseconds in the 5 days. It was about 23 teraflops of computation. So that was, and they felt this is really, this is giving us the crystal formation we thought we would see, but that's what the computing is needed for this really small volume, 2 nanoseconds. So it's sort of off the scale, and that is another argument for doing abstract universes and trying to cut corners too. But the EvoGrid project is really all about the discussion right now and about frameworks. And we may conclude, somebody may actually take out an envelope or a back of a napkin or a placemat and do the math and determine this is just not going to happen in our lifetimes, and I'll have to wait another 25 years. I'm reminded of the discussion between Lauren Carpenter and I believe Alvy Ray Smith and the folks at this was before Pixar, this was at Lucasfilm. They were at a restaurant somewhere in Marin, and they turned over their placemats and they said, we want to make a full-length 2-hour animated film. We think we can do it. We've got these machines. And they were just kind of conceiving of RenderMan as their hardware software platform. And they did the math, and it's like 30 frames a second and this much storage we need on disk and this much processing to generate each frame and blah, blah, blah. And they looked at each other, even with Moore's Law and everything and other things, other magic in the future, 25 years. It's going to take us 25 years. And those guys, that core of guys, went off and formed Pixar, Steve Jobs, and they started working and worked throughout the 80s. And then in the early 90s, they had developed grids, basically, server farms, render farms, rather. And then in 1992, 93, they decided they're going to do Toy Story. Production, I guess, finished around 94 or so. It was only 60-some minutes long. They cut all these corners, and they used the server farm and everything, and they did it. It's like, it only took us 16 years instead of 25. And so that kind of the back of the envelope calculation needs to be done for this project. And I invite anyone in this room who is good at envelopes. But it may be that we can accomplish something in 25 years that is of value. That's the concept.
Well, I just noticed this, I know the life that's on this planet has evolved, and we're 40,000 feet off at any point in time, except for, I guess, 9/11. And we can reproduce there. And there are some delta functions where we are higher. But basically, that's as far as we've gotten. And it's based on a requirement to come back and resource at the substrate.
I guess I'm a little skeptical. It's easy to imagine problems and algorithms where it would take 10 to the 100 years to solve the problem. And you know, you're talking about, you know, all these computers to do 2 nanoseconds of a little cube. The Earth had a huge volume and hundreds of thousands or millions of years to evolve life. Why do you have any hope at all that you could possibly do it?
Hope springs eternal, because I'm a nerd. I believe. Well, I think that the journey is going to be more rewarding than the destination, in that if we can get something large enough going where we actually see ratcheting occurring, where we actually see, you know, because looking at artificial light stuff for the last 20 years, even since Barricelli back at the Institute on the von Neumann machine, you know, those little simple universes sort of, they get some really neat phenomena that happens, it crowds out, it caps out and stops. And there's never anything that comes on top of that. Tom Ray's Tierra had the same phenomenon. They kind of fill up the space, the local maxima or whatever. We can show that in a simulation space that we can do a ratchet where you can see, oh, a bunch of goopy goops formed, but then it kind of half broke up and then something else formed on top, and it's a little more complex. It will give us a real kick in the pants, in a sense, for the 21st century to say there is a way to test theories of emergence. There is an emergent science that, you know, and there's a discovery system. There's an experimental discovery system that we are seeing the beginnings of, and it may be valuable to just even getting that far, ratcheting through 2-3 levels of complexity and seeing structure emerge, even if it's never Darwinian natural selection ever occurs in there. There would be, I would propose, another version of the EvoGrid. One version would be the Origins edition, which you can't touch, don't touch the black box. You know, it's an experiment. The other one would be the Intelligent Designer edition. The Intelligent Designer edition will allow you to go in, make your macromolecular structures, and say make 50,000 copies of this and shove them in and try to get the thing going. You know, of course, for real chemists, it would be, I want to simulate a cell wall, a certain portion of a cell wall, and I want to put cholesterol across it and see if I can get something realistic. So but there would be the ID, the nerds are hacking this and trying to make something happen. And perhaps in the ID edition of just people messing around, not tabula rasa emergence, we might find something there too. So in a sense, it's trying to create a new discovery system.
And for the intelligent design version, you'd give yourself a limit of 4,000 years, perhaps.
There you go.
Right.
Yeah.
Bruce, as a memento of your talk here, you have something that you can place your next quantum computer on. It's that small, goodness. But hopefully you can wear it with pride at the next Burning Man conference.
Is this computronium or unobtainium?
You'll have to test it when you get your EvoGrid working on it. Will you join me in thanking Bruce Damer?